In this video, we're going to review what is called calorimetry. So this term up here, calorimetry, this is a method that is used to measure the enthalpy change of a reaction. And this is noted because we cannot know the exact enthalpy of the reactants and products. So instead, we measure the change. And this is done using that term here, calorimetry, through measuring a change in temperature. So we're going to see this delta T as part of a calorimetry utilized equation. So let's first define a couple terms here. The first is heat capacity. And heat capacity we'll define as the amount of energy required to raise the temperature of a substance by 1 degree Celsius or Kelvin. Since both the Celsius and Kelvin scale increase by the same amount, we could say either. And then down here, we have this term of specific heat capacity, sometimes just simplified to specific heat. This is the amount of energy that's required to raise the temperature of specifically 1 gram of a substance now by 1 degree Celsius or Kelvin again. So same type of definition, but now this specific heat capacity refers to a specific quantity, that of 1 gram. So there's a table shown here of some specific heats of substances at a temperature of 298 Kelvin. So we can see here some gases over here. We have N2, then we have some solids, some metals, liquid mercury. So all different phases over here and some corresponding specific heat values given in the unit of joules per gram Kelvin. Again, that's interchangeable with the unit of joules per gram Celsius because the temperature increase is by the same interval. Then we see over here, which we will utilize quite often, the specific heat capacity for liquid water. So in some aqueous reactions, liquid water is a medium, and we might need to know the specific heat capacity of liquid water. So this value, 4.18, sometimes 4.184 to another significant figure is used. And again, that's shown over here. So this is a very common conversion factor when we are measuring something in calories or joules, and we need to get to calories. So we can see here that the specific heat capacity, that energy here that's needed to raise the temperature of 1 gram, right? So we have 1 gram of liquid water down here, 1 gram of liquid water up here, but the temperature goes from 14.5 to 15.5 degrees Celsius. So it took exactly 4.184 joules to raise that temperature by 1 degree. So we're asked here to give it some thought and look at table 5.2. And we want to know which substance would undergo the greatest temperature change, so the greatest delta T, when the same mass of each substance absorbs the same quantity of heat. So Q and M are constants, right? These are the same values for either substance that we're comparing. And what we could consider is that the lower the specific heat capacity, the greater the temperature change. And if we were to equate here, Q is equal to the mass times the specific heat capacity, C, and then the change in temperature. This equation is where I came up with that summary that the lower heat capacity would have the greater temperature change, because we know that if we set two of these values equal, we know that Q is constant, and we said that mass is also held constant. And the only thing that is different would be the specific heat capacity. So if we have a lower value for that, we would see a greater temperature change, because if we looked at another substance with a higher specific heat capacity, we would see a lower temperature change if we wanted to keep this an equality. So again, something like mercury, we would see a greater temperature change than in water because of the difference in specific heats. So let's look at sample exercise 4 here for the remainder of this video. And we're told that we have a large bed of rocks, and this is used in solar heating homes to store heat. So that's the purpose of these large rocks. And we want to assume that the specific heat capacity, so the C of our rocks, is equal to 0.82 joules per gram Kelvin. And we're asked in part A here to calculate the quantity of heat, so the Q, that would be absorbed by 50 kilograms of rocks if their temperature were to be increased by 12 degrees Celsius. So we're going to use that equation that I wrote out above, Q equals mc delta T, and we're going to plug in some values here. So due to the units of C, our mass will have to be in grams. So I'm going to multiply 50 kilograms by 1,000. So I'm going to plug in 50,000 grams to this equation. The specific heat capacity is given as 0.82 joules per gram Kelvin. And I know that that's the same as Celsius. And then I'm going to solve for the change, or rather, I'm given the change in temperature of 12 degrees Celsius. So I'm just given that value. I don't have to solve for my delta T. So I just plug in and then multiply each of these values. So I'll solve for Q here. And again, this would be the quantity of heat absorbed. So this is going to be a positive value, 4.9 times 10 to the fifth joules, if we round to the correct amount of significant figures. And then we see in part B here, we're asked to find a temperature change. So now we're asked to solve for delta T, but we're going to use the same equation. We're just going to rearrange it. So here's that original form again, Q equals mc delta T. So if we want to solve for delta T, we're going to end up dividing Q by m times C. So let's plug in those values. And we're told that the rocks are emitting 450 kilojoules of heat. So that value is given in kilojoules, but again, due to my units being joules per gram Celsius or Kelvin, I'm going to convert this to be joules instead of kilojoules. So that will be 450,000 joules. And now I'm going to divide by that same mass. So that would be 50,000 grams. And my specific heat capacity of 0.82 joules per gram Celsius. This will give me my temperature change in either Celsius or Kelvin. And when I plug this in, I know that the rocks are emitting heat, so they're going to be losing energy. So this will be a negative change in temperature of 11 degrees, whether it's degrees Celsius or Kelvin.